Okay, so we are still in Chapter 2, and we are at Section 5, and in Section 5 they are talking about a motion of an object that's undergoing constant acceleration. So all of the problems in our course will deal with constant acceleration, meaning whatever acceleration the object is traveling with, there'll be a constant acceleration for a certain amount of time. In real life, you can accelerate and you could change your acceleration rate by stepping harder on the gas pedal or by tapping on your brakes or slamming on your brakes. The acceleration or deceleration rate changes quite a bit. But in our problems, we'll have constant acceleration rates. So for all of the word problems that's going to be coming up, what's going to happen is there's going to be a beginning to the problem and the end to the problem. And the way I've written the things here is we'll have a beginning velocity, the initial velocity, v subscript o, it's a vector. So the problem will start where the initial velocity is happening, and the problem will end where the final velocity is happening. And all the standard units should be used at this point, so meters per second is a standard unit for both velocities. So sandwiched between the beginning of your problem and the end of your problem are the other three letters we've been working with. We've been working with delta x, called the displacement. So if it's a car driving down the road, at the beginning of the problem, we have a certain velocity. At the end of the problem, we may have a different velocity. The car has moved through a certain displacement. The car may or may not be accelerating. It may be moving at a constant speed and such that the acceleration would be 0, but it may be accelerating at some number. So during the beginning to the final, we'll have some number for acceleration. And also, time has to be moving. Time has to be passing on. So between the beginning and the final, we'll have something dealing with time. All of these things are vectors. The vectors are simplified with the arrow over them. And the thing that's not a vector is this thing called time. Time is a scalar. There's no direction associated with time. It's always just moving forward. So we're going to now derive equations to use with constant acceleration problems. So we'll start by the definition of acceleration. So acceleration is defined acceleration equals delta v over delta t. And we went and we changed that, and we called that v final minus v initial over t. So if we call this the acceleration, well, what I'd like to do is I'd like to go and rearrange this formula. So if we rearrange it, let's just multiply both sides by t to get rid of the denominator. So if I multiply the right side by t and the left side by t, this cancels out. So I'm left with a t equals v final minus v initial. If I end up adding v initial to both sides, I will get this. On this side it cancels out, so the only thing I have on this side is v final. And what I have on this side would be v initial plus a times a t. And that's how we end up getting the first formula of our 4 formulas of constant acceleration. And this formula, it's typically written in this manner. So there's going to be 4 formulas of constant acceleration, and this is the first one of them. And I showed you how I derived it based on the definition of acceleration. So I said earlier in the talk, the average velocity equals your displacement, delta x, over the time. But now I'm telling you there's another way to get average velocity. Another way to get average velocity, if we are in fact undergoing constant acceleration, another way to get average velocity is take the 2 velocities, add them up, and divide by 2. So we could take our beginning velocity plus our final velocity and divide it by 2. Okay? And if I look at these two, since the left-hand side of both equations are equal, I can set the right-hand side of both of these equations to be equal, and then just solve for it. So if I do that, I'll get this. go and I rearrange this and multiply both sides by t, I could get a formula that will look as such. So let me write that formula up here on the top left of the board because I'm trying to keep the four formulas of constant acceleration with each other. So I will say okay, so that's the second of the four formulas of constant acceleration. If I take this equation right here and I substitute in where it says v final, if I substitute this piece from the first equation, I'll get a new equation. So let me show you what I mean. If I take this second equation, I'll have this. So delta x equals 1/2 v initial plus. Now, instead of writing the next piece, I would like to use what does v final equal? So v final equals v initial plus a times t. And you see, and now I close the parentheses and I put that t right there. Okay. So if I expand on that, I end up getting a new equation. So why don't I just stay in the parentheses for a minute? So it's 1/2 v initial plus v initial is 2 v initial. Oh, nope. Alright. Plus a times t. And I have this thing here, t. Now, why don't I simultaneously multiply everything by 1/2? So, 1/2 times 2 cancels out. So this becomes v initial plus 1/2 times a t becomes 1/2 times a t. And then I'll end the parentheses, and I still have this t there. And now why don't I multiply everything by t? So it comes out to be v initial times t plus 1/2 a, and I have the t here, and I multiply it by another t, I'll get t squared. Okay. And that's a new formula. That's our third formula. So if I write that one down, I get something like this. So that formula is showing us delta x equals v initial t plus 1/2 a t squared. Okay, and there's another one. I mean, you can basically keep on deriving new ones. You take the previous formula and you can just go and rearrange this thing for another symbol and plug it in and see what you start to get. So I can show you how to get the next one. If I write the last formula that I've done, so if I write this formula here, what it was delta x equals v initial t plus 1/2 a t squared. Now, what I could do is I could now go and plug in this first formula. So you see the first formula, but I want to solve that first formula for t. So how would I solve this first formula for t? If you rearrange it, you'd get that first formula to look like this. You would say, let me go on further. You would say this: t equals v final minus v initial over a. Okay? So I could expand upon this formula by plugging in the t's. So it would be delta x equals v initial, and now for the t, I would say parentheses, v final minus v initial over a plus 1/2 a, and then it would be v final minus v initial over a again, and you have to square that. Okay. That's not a trivial thing to do. So I am going to let you enjoy trying to derive that for yourself. It's in the book on how to derive it, but what comes out of it is another formula. And so the final formula up here will be, I'll write it to the left, V final squared equals V initial squared plus 2A delta x. Okay. So what you can see in the boxes here to the left are called the four formulas of constant acceleration. So we have the four formulas of constant acceleration, and when we do a word problem, we're basically going to be using these. We'll use these formulas in chapter 2, we'll use these formulas in chapter 3, we'll use these formulas for the rest of the chapter. So the way it reads is, you have a word problem at the beginning, and there'll be some givens. These are the 5 givens that can be involved in any physics problem. So of the 5 physics formulas, the 5 physics things, so we have, out of the 5 things, we have V initial, we have V final, we have the acceleration, we have the delta x, the displacement, and we have the time. Those are the 5 different things. So this is the initial velocity, this is the final, this is the acceleration, this is the displacement, and this is the time. Okay, so of those 5 things, when you read a word problem, you'll usually get 4 things. There'll be 3 things which will be given to you, and there'll be 1 thing that you're going to be looking for. So if you just look of those 5 things, there's 4 different things in each of these formulas. This one does not have delta x. So this one is missing delta x. And this one right here is missing the acceleration. And this one right here is missing the final. And this one down here is missing time. So they all have there's only 4 things here missing. So we're missing 1, 2, 3, 4 things out of these 4 formulas, but they all have the initial velocity. So every single one of those formulas there have the initial velocity. So what your job would be is to try to find out what the 3 givens would be. So you'll do a formula, you'll do a word problem, and you'll read it twice to get it accurate, and you'll find out the 3 givens and the 1 thing you're missing, and then only one of these formulas is going to work to be able to plug it in. So here's a word problem, and the word problem says, so this is an example, the word problem says there is a car, and the car is traveling at 10 meters per second, and then the car is going to accelerate at 3 meters per second squared for 4 seconds, period. The word problem's over. It asks us 2 things to find. So it says to us, find the final velocity of the car. What they mean is, find the final velocity after these 4 seconds have passed, and B, find the distance the car has traveled, again, after these 4 seconds have passed. How far did the car become displaced? So a few minutes ago, you saw 4 formulas of constant acceleration, and at this point you have to start using them. So what I typically try to do is write down the givens, and then write down what I'm being asked for. So I'll do either part A or part B first. Okay. So I'll write down the givens. The initial velocity is 10 meters per second. It says it right here. They said the car is traveling at 10 meters per second. It tells us right here it accelerates at 3 meters per second squared. So the acceleration is 3 meters per second squared. It says right here for 4 seconds, so the time is 4 seconds. And it's asking us to find A. The first thing it says is find the final velocity. So V final equals question mark. So of those 4 formulas of constant acceleration, we definitely have a a formula that relates to these things right here. And it was the first one that I just put on the list a few minutes ago. So the formula I would use would be written this way. And I would just plug it in. So V final is going to be 10 meters per second plus 3 meters per second squared times 4 seconds. So what I've just done is I've just plugged it in. So the initial velocity was 10, the acceleration was 3, and the time was 4. And if I plug all those things in, it comes out to be this. And 3 times 4, as far as the numbers go, it's 12. As far as unit goes, this is written this way. It's meters over second squared. And this is written as seconds basically over 1. So second squared times, in the denominator, times a second, one of these units will cancel out. So this will just be left with meters over seconds. Which is a good thing because we did dimensional analysis in Chapter 1, and you cannot add two different terms if they're not exactly alike. This is 10 meters per second. We have to add another unit of meters per second. So 10 plus 12, and the unit's meters per second. The final velocity comes out to be 22 meters per second. Okay, and that's how to do part A for that particular problem. So we now know that the A piece came up with an answer of 22 meters per second. And what about the B piece? So what I've done is I've written in the V final because we know what the V final is. So the V final came out to be 22 meters per second. We can use it if we like. We don't have to use it if we don't want to. They're saying find the delta x here. So if we don't trust this V final, we don't have to use it. We could use a formula that looks like this. That's one of our 4 formulas of constant acceleration. Delta x is what we're looking for. V initial, we have it. Time, we have it. Acceleration, we have it. And time again, we have it. We can just plug it in to the 3 original givens. So we could say V initial was 10 times 4 seconds plus 1/2. The acceleration of this thing is 3. And the time was again 4. And we have to square that whole thing. So 10 times 4, the number comes out to be 40. And the unit, meters over seconds times something with seconds. The seconds cancel, so we're left with meters. Plus 4 squared is going to give us a number 16. So the number is, let me just write this out. So this is 1/2 times 3 meters per second squared. This comes out to be 16 seconds squared. We have to multiply the number, we have to multiply the unit. So 16, now you multiply 16 by 1/2 and you'll get 8, and you multiply 8 by 3 and you'll get 24. So this unit, this number here comes out to be 24. The units of meters over second squared times second squared will just be left with meters. So this is going to be 40 meters plus, and I said 24 meters. So if you add those two numbers together, 40 plus 24, you get 64. So here's the answer for part B, and over here is the answer for part A. And that's how to do that particular problem. Okay, so here's a word problem, and it says that there is a car, and the car is traveling at an unknown speed. And then it says the car is going to accelerate for 5 meters per second. The car is going to accelerate at 5 meters per second squared for the next 10 seconds. And then it says it's going to accelerate that way to a final speed of 60 meters per second. Now that's a really fast speed. That's something like 120 miles per hour on our, with our units. So that's going fast. And then it says find the displacement of the car during those 10 seconds. So how far was the car displaced from the time it first touched the accelerator on the car and started speeding up more? Okay, so if we write out our givens, just read it. Car is traveling at an unknown initial speed, so I might even put V initial is unknown. The car accelerates at 5 meters per second squared, so that's a given. The acceleration is 5 meters per second squared for 10 seconds. So 10 seconds, that's a given. That's a time. And it tells us the final speed is 60 meters per second. Okay. And the real question is, find the displacement after those 10 seconds. So they really want us to know, find the displacement. So delta x is what we really want to find out. If you try to look at those 4 formulas of constant acceleration which I've written, you can't do it with, you can't do this problem. If you try to only look at these 4 things here, there's no formula in those in the list that I gave you of having these 4 variables in it. Every one of those formulas that I gave you has an initial velocity. So the only way to do this problem is to actually find the initial velocity first. So I'm going to say find V initial first. Okay. And the only reason why I'm doing that is there's no other way to solve for delta x. So for a moment, let's pretend we don't care about delta x. Let's say with these 3 givens they've given me, the acceleration, the time, and the initial final velocity, let us find the initial velocity. So the formula I would use would be this one. V final equals V initial plus A times t. Those are all vectors except for the time. Plugging it in is going to give me this. 60 meters per second is V final. V initial is unknown. A is this number 5. And t is this number 10. So if I simplify, this becomes 60. This is V initial. This becomes 50. And meters over seconds, that's a squared, times seconds will be just meters over second. And if I subtract 50 from both sides, what I end up with is 10 meters per second equals V initial, and this cancels out. So 10 meters per second equals V initial, and that is my starting speed. So you see, I can't solve the problem the way it's written with the way it's written. I have to find something first. So let me change this. And let me write this now is 10 meters per second. And you see, now with these 4 givens, I can find delta x, and I can use different formulas. There's no one formula to use here. So I can use many different formulas. So I'll use a formula that I haven't used yet in a sample problem. I'll say this. Delta x equals 1/2 V initial plus V final times the time. And I'll just plug it in. Delta x equals 1/2. V initial is now known, 10 meters per second, plus V final, that's also known, 60 meters per second, times the time, and that's known, and the time there is 10 seconds. Okay, so if in the middle here you do this, that becomes 70 meters per second. So 70 times 10 comes out to be 700, and that would just be meters, and then you take half of that, you multiply it by a half, and you'll get 350. So delta x, you can use a calculator and just plug it in. Delta x will come out to be the number 350 meters. That's how far the car traveled from the first moment that it hit the accelerator. So it was traveling at a speed, up here it says it was at an unknown initial speed, but now we know it was 10 meters per second. So it hits the accelerator, and it'll travel a total distance of 350 meters during that time. So here's another example, and they're getting more difficult as we go along. So this one here says we have a car, and the car is traveling at 10 meters per second. That's approximately 20 miles per hour in our unit. So you have to kind of get a feel for how to relate meters per second units to something that you can actually relate to in our life, meaning miles per hour. So it says the car is going to accelerate at a rate of 2 meters per second squared. So they're going to step on the acceleration harder, and they're going to start to speed up. find the time involved for the car to travel 150 meters. Okay, so if we write out our givens, this is what we'll have. So I'm sorry, I'm thinking myself. So as I write out the givens, I see the car is traveling at 10 meters per second, so that's my beginning velocity. So V initial is 10. It says the car accelerates, and once the units too, it'll tell you that's 2 meters per second squared. That's an acceleration rate right there, 2 meters per second squared. It says the car will travel a total distance of 150 meters, so that's delta x. And the thing they want to know is how much time is involved. So find the time. So they're asking us to find time. So if you're going to use those four formulas of constant acceleration, just plug everything in, what you're going to get is this. You would pick this formula. Okay. If you try to plug everything into this particular formula, you're going to get something that looks like this. And that may look fine to you and easy to solve, but there's no way that you can solve for two different powers of 10. This is 10 raised to the 1 power, and this is 10 raised to the 2 power, without using something called the quadratic equation. Now, if you know the quadratic equation or fine with the quadratic equation, use it. But for a lot of students, this quadratic equation becomes a mathematical roadblock. Okay? It becomes an obstacle that they can't actually figure out. So I've seen many students trying to solve this type of a problem here, and they come up with an error. They come up with a mistake because they don't remember or they forgot exactly how to use this quadratic equation when you have trying to solve for two things which have different powers to them. So what I would say is don't get stuck with the mathematical roadblock. Why don't we work our way around it? So how would we do that? Why don't we do this? For the moment, let's find V final first. Okay. The problem didn't say what is V final. The problem didn't say find V final. We don't really care what V final is, but we do care if we cannot solve this math equation. So the math shouldn't stop us from solving the physics word problem. So we want to solve this math equation. That's going to maybe stop us. We can find V final first. So that means I'm not going to use this equation. Now, if you feel fine with the quadratic equation, then solve it. And you'll get the answer. You'll get two different answers for t because the quadratic equation will give you two answers. Most likely one of those answers will be a negative time, which doesn't exist. So if you got two answers out of this, throw away the negative time and keep the positive time, and that'll be the answer. But I'm going to work around about it. I'm going to say this. If we wanted to have these four things in one problem, which formula would we use? And we would use this one. Okay, and with those four things, I can just plug in what I have. So I can say the initial velocity is 10 meters per second, and I got to square it, plus 2, the acceleration is this number 2, delta x is this number 150, so I can just now keep on working. So 10 squared, I have to square both the numbers and the units, so it's 100 meters squared over second squared, plus 2 times 2 is 4, 4 times 150 is 600. So this comes out to be 600, and the units again, meters times meters is meter squared, divided by second squared. So this is going to come out to be 700 meters squared over second squared, and that's what V final squared is. So I have to use a calculator and take a square root of that. So when I take a square root of that, on my calculator screen it says this, 26.46. So V final is going to come out to be 26.46 meters per second. Okay, so I'm halfway there. They wanted me to find how much time was involved. I'm finding V final first to try to make things a little bit more easy in my life, and I've just figured out that the final velocity is 26.46 meters per second. So now I'm going to use that as a given. And with these four givens, now I got four things. With these four givens, I can now go and I can find the time. And that's the real question. How much time was involved? Okay, so that's what I'll do. I'll erase this equation over here, and I'll just write a new equation. So with these four givens, I can use almost any formula I want. I don't want to use that one that led me towards a quadratic equation, so I'll use something like one of the first ones. V final equals V initial plus A times T. V final came out to be the number 26.46. V initial was the number 10. A was the number 2. And the time is what I don't know. So when I plug this in, we'll subtract 10 from both sides first. So this becomes 16.46 meters per second equals, that's gone, 2 meters per second squared times time. I'll divide both sides by 2. So 2 meters per second squared is gone from this side, and over here it's going to be 8.23. And if you take meters over second and you divide it meters over second squared, the only thing that remains is the second piece. And that's what time is. So time is going to be this. So that's my final answer. The car is accelerating for, that's an 8.23 seconds. And the car is accelerated at that rate and has traveled this distance for 8.23 seconds. So that's how to do that particular problem. So sometimes the problems are not as easy as you may like. Physics, most of the word problems are tricky. You have to read the word problems with a lot of care. You have to try to visualize the word problem in your mind and evaluate the results. Does it make sense that this car should be accelerating for 8 seconds? Well, 150 meters traveling, and 100 meters is about the length of a football field. So does it make sense that this is a very, very small acceleration rate? What this really means is every second that passes, that car will be going faster by 2 meters per second. Okay? So does it make sense that the car should be, right here it says it's 8.23 seconds. To me, it makes sense. You're going to be traveling past approximately... You're not going too fast at the beginning. This number here in our world is approximately 20 miles per hour. So it's not going at incredibly big speed. So read your word problems carefully. I suggest you always read your word problems twice. I suggest you always write down the givens. I suggest that you check that the givens have to be converted if they're not in standard units. And evaluate your answer and see if it makes sense to you.